Watch Mr. Wizard. That's what all the kids in the neighborhood call him because he shows them the magic and mystery of science in everyday living.
Wizard.
Oh, hi, Irene. Come on in.
Hi.
Run around over here.
What are you doing?
Well, you see that stopwatch or big clock?
Mm-hmm.
See what it stopped at?
16.
About 16. And you see that dark liquid?
Yep.
Well, that's sitting in front of a little thing here. If I put this in front, now notice what happens to the clock.
Well, it's moving.
Yes, the clock starts. Would you take, see, I have these little paper cups, like they have lemonade and picnics. Mm-hmm. One of them's dark color, blue, and one other is yellow,
Yeah.
lights. Would you pour those two together? But before you do, I want to bring this clock around, and I'll start the clock the minute you pour. Go ahead.
Okay. You know what's supposed to happen? Is this that?
Well, you'll see.
Then
You
it should
watch
be
that.
black. Well,
What was that former time?
oh, 16.
Didn't stop the clock. Was it about 16?
Yes.
16 or 17?
Yeah.
I have to hold it tight up there. Okay, now, you said it was supposed to turn black, and it did. But notice that it turned black 16 seconds after you
I
poured
know.
the two together.
Not the instant I did, the same time as the other one.
Okay, well, later on, you're going to be able to mix those two solutions together and vary the time to be anything you want. You want it to go in 20 seconds? You can do it. 5 seconds? You can do it. You not only will be able to do that, but you'll be able to predict what time it's going to go in, even if you haven't chosen the time. Because this is a special kind of form of chemical reaction or chemical change, and that's what we're going to investigate today. Maybe when we begin, you ought to tell me, what is a chemical change?
Chemical reaction.
Yeah.
No, but it's when you have like two chemicals
Mm-hmm.
and you mix them together
Mm-hmm.
and they form something else.
Well, maybe I better do that and see if that'll fit your definition. Here are some household chemicals. They'll work, won't they?
Yeah.
Here is one, and it is sodium bicarbonate. Chemical?
Mm-hmm.
Okay. Here's another one, tartaric acid. A chemical?
Uh-huh.
You call it cream of tartar.
Right.
Okay. I'll put about a teaspoon or so of that in. Okay, now you said put two chemicals together, and they produce a chemical change.
Mm-hmm.
I don't see anything. Powder.
That's not a chemical reaction. These are like just next to one another.
Well, that's what you said I should do, didn't you?
But in chemical reaction, the chemicals they go into one another like, and they form something else.
Well, would you try to take these apart? Would you like to try that? I think they're pretty
No.
close.
They're pretty close, but they didn't form something else.
How do you know? They formed a white powder. There's got.
But it was right before.
Oh, I see. What? Oh, what do you mean by a chemical change then? Maybe we better define that. How do you know when something has reacted chemically?
Oh, wait, it gets different.
How do you mean now different?
Well, heat is given off,
Might get hot.
color changed,
Yes, could change color. What else?
smoke.
Smoke or gas or something like
Yes.
that. Yeah. There are a couple of other things too. Well, there's no chemical change here then. Nothing
No,
happens.
you're just mixing them together.
Well, what would you suggest I do then? If you said that I should mix two powders together.
Add water. Add water.
All right. Can I do that? Before we add the water, however, I would like to put in a little detergent. We'll see why. Okay, you want to stir and I'll add the water. Is a chemical reaction taking place? Hmm?
I think so. Yeah, yes.
Why? How do you know?
Well, it changed colors.
Yeah, well, of course, that could be simply because we're stirring it up. Now, see those bubbles?
Mm-hmm.
Think that's just from the detergent?
Maybe that's the chemical form.
No, see what's happening? In other words, if you put in just plain detergent into water, I'll add a little more to make sure that we're getting enough. Hang the expense. Now let's begin. How do you know that there's a chemical change taking place?
Well, because there's another something else is
What?
forming.
What?
The mixture of the two.
The gas.
Oh,
Yeah,
yes.
see, the gas. Those little bubbles.
Oh, look at it.
You know what those bubbles are filled with?
No.
Yes.
Yeast gas?
Yeah, well, no, that's right, yeast gas.
something?
It's carbon dioxide. And what we have just made here is baking powder. You know the stuff they put in baking powder biscuits and
Yeah.
cakes?
Yeah.
We had a little detergent, so I wouldn't suggest you do that if you make a cake.
No.
But we did it because we didn't have any dough to capture the bubbles. So what we did was we mixed two chemicals together, but nothing happened. When we put water, a chemical change took place. Gas was given off. That fits your definition, okay? Well, now let's try the two powders that I used to make that black stuff. You know, that chemical change that took 16 seconds to do?
Boy, look at it, the way it's coming over.
Yeah, it's certainly going all over the place. Here. I want to get a beaker to do them. And you look at those two powders, see what they look like.
Well, they're both white. There's nothing actually different about them. They're both white, and they're both grains.
Well, here, mix 2 teaspoons of each in there.
Same spoon?
Well, it'll be all right. That's not very good scientific practice.
There.
Okay, now shake them up. Mix them up good.
All mixed.
Nothing happening? Any chemical
No,
reaction?
no.
What do you think we ought to do?
Add water.
Okay, just put a teaspoon of water in there.
Teaspoon?
Yeah, that's enough. Let's just start with it.
Boy,
Beautiful.
purple gas.
Yeah.
Just
Well, it's not really gas. It's
smoke or something?
purple iodine vapor.
Iodine?
Yes. The little box, or the little paper cup that's blue like this has iodine compound in it. And when you put water on it, did it react?
Sure did.
It sure did, didn't it?
Gee.
Now, if I say there's iodine present, how are you going to prove it? How do scientists test for
I
iodine?
know.
Huh.
You put it on a piece of bread.
What? You make an iodine sandwich?
No. You test it for starch. You put it on bread and it turns black.
Oh, well, we don't have to have bread, do we? We just have starch.
Oh, yeah.
Yeah. Well, now, this has some iodine in it. And in order to prove it, let's let it settle a bit, get down so we can pour off some. Pour some in here to dilute it, then we'll add starch. I'll get the starch.
Okay. Is it hot?
Well, not too much, but chemical reaction, so
Makes it hot.
now let's dilute that so we get it nice and light. Okay, now you can see through it all right? Now, if there's iodine in there, what's it going to do when we put
It'll
starch in?
turn black.
Okay, put some starch in there. Well, we're mixing up, hold it, you're mixing up everything. Here's a clean spoon.
Okay.
Did it?
Well, it certainly turned black, so that's
Now-
iodine.
That's the another chemical change, by the way, color change.
Yes.
Now, that's the reaction that we're going to do over there with those two solutions when you put together. We're going to get iodine free, and we're going to have starch present, so when the two get together, it turns black, or really very dark blue. Now, what other things happen that affect chemical changes, besides obviously putting them in water? If you wanted to speed that up, what would you do to it?
Oh, well, you could heat it.
Why would heating help?
Because then the molecules move around faster. They can bunk into the other molecules, make them move faster, and it'll...
Well, do
Do
you
it faster.
suppose then that if we have hot and cold solutions, we will have a difference in time over here instead of the 16 it was before? Let's try it. What was the last one?
It was,
16?
16.
All right. Let's try it now. And with cold solutions this time. Remember, the beginning was 16. Oh, before we do that, we should probably take the temperature of this thing. Let me get my thermometer out. I think you used this electronic thermometer once before, didn't you?
Yes.
Let's do this again, and this time, check the temperature. All right?
Mm-hmm.
One of each. Clock is going. Okay, whenever you're ready, you pour them together.
Okay.
Go ahead. I start the clock as soon as those two solutions touch. Stir it up, make sure it's And you read that temperature.
It's 72.
There she went.
Yep, there she went.
16 seconds at
Around 72.
70.
70.
On 70
there.
degrees? All right, now come up back here because I have a chart all set up for you. Here's the pencil. See what this says here?
Temperature. Oh, and this is time.
Those are in seconds. All right, so what would we find now as the result of our first test?
Well, it took 16 seconds.
Yeah.
It's down here.
At about 70?
At about 70.
Okay.
Down here.
Now, let's say we go down to, let's go up first. Let's go up to, say, 110 or 120. What do you think will happen? Which way should it go? Should the next mark be on this side, or should the next mark be on that side?
This side.
Should be over on that side, if your theory
Say
is correct.
less time.
All right, let's try. See if you're right. Now, here are two small glasses. We'll put one of each in there. Now, I have two little immersion heaters so that we can heat them up very fast. See? So you put one in, and you hold them in there, and you stir them up. And I want to get some water and wash this thing off. I'm afraid that if I keep putting it in the same solution all the time, that we may, contaminate it. So I'll give it a quick rinse. Okay. Now, I'll turn the switch on, and we'll start heating up those two, and we can check the temperature here. We ought to stop. Keep stirring them up. You stir that one up, too. Going up?
Mm-hmm.
We ought to heat them up till it gets to about the end of the scale. That's about 120, isn't it?
Yes.
So let me know when it gets to about 115 so we can stop. It'll coast probably that much further.
Well, it's staying at around in the 80s.
Is it hot? Yeah, there it moved, didn't it?
There now. It's above 90. A 100.
100?
It's going up.
It's going up. All right, I'll get a glass ready. There, 115?
110.
Okay, let's stop it there. Give them a final swirling around.
Take this out.
Take that out. Okay, now put the thermometer in here, and you mix those two together. When you're ready, I'll start the clock. Go ahead.
Here goes.
According to your predictions,
Should happen very quick. Hey! Did it already.
about what?
9.
Okay, put it down on the chart. Oh, what's the temperature?
It's around 110.
Okay, 110, 9 seconds.
So I was right.
Yeah.
9 at around 110.
All right, now let's cool it down to about 50 degrees. What's it going to be? Faster or slower?
It should be slower.
So it should be...
If this is right,
Yeah,
it's
well,
like my...
if you were going to continue that line, where would you predict that it's going to be?
Around over here, maybe?
Really? You think that line goes like that? In other words, you'd have to, continue on a straight line down like this.
Okay.
That's the way you should. That's the way you
All
should read
right.
the graph.
Around 25.
25? All right. You want to clear that one out, and I'll bring some up from the refrigerator.
Are they good and cold?
Yeah, pretty cold, I think. We'll find out when we mix them.
Yep.
Okay, whenever you're ready.
Okay, here goes.
Now, you're saying what?
Bet it'll take longer.
About 25, you said, as a matter of fact. Well, you've now passed safety...
Yep, that's where it originally went. There's 20.
Didn't turn off either, by the way.
No,
But it was about
that-
27?
Yeah.
Okay, you want to put that
27.
down on the chart?
Uh-huh.
And what's the temperature?
It's around 40.
Okay. Oh, 40. No wonder. You're going off the chart, so you have to pretend that 40 is down here, and at what?
At 27.
Okay, so it'd be about
So
down
it's
there. So you want to draw a line up there like that?
So. Not very straight.
Not very straight, but now you can see. Now, if you, I said, I would like you to have this reaction take place at 15 seconds. Oh, no, 10 seconds. What would you do?
Oh, I'd make it go to around
110 degrees.
110
Yeah.
degrees.
If you wanted 12 seconds?
I'd have to make it go around, yeah.
So you were absolutely right, weren't you? The hotter it goes, the faster it goes.
Uh-huh. And then
Now-
you can really tell.
Now let's try changing the concentration. Before, we just had 1 and 1 all the time, didn't we?
Yes.
This time, let's try doubling.
2 and 2?
See that glass is marked 2Y,
Yes.
2 yellow, and here's 1 blue.
Mhm.
You mix them together here now. And tell me beforehand, what do you think it's going to be? 2 yellow and 1 blue. We had 1 and 1 before.
Yeah. I don't think it'll work. It
Well,
won't
try
work.
Go ahead, try it. Ooh, I started a little early. All right, there.
It won't work because there's very little of the blue, and if it mixes well with that same amount of yellow, how can it mix with the same amount?
15,
Two
16,
amounts.
17, 20, 25, 30, 31 or
Ten.
2? Ah.
Well, I was way off.
I have another chart up here for you. Let's get that chart started and see what happens here. Can you fill it in? Blue and yellow, you see. 1 to 1 was what? 16.
Yes.
So put a mark in there for 16.
Down here.
Now we had 2 yellow and 1 blue. And what happened
So-
here?
Oh,
2 yellow and 1 blue.
And that one went around.
31 or 2. So put
Yeah.
a mark there, and I'll go set it up for the next one.
Okay. There.
Now here's 2 blue and 1 yellow.
Uh-huh.
Okay, dump them together. Tell me what you think it's going to be. Go ahead.
I think maybe it'll take less time if
Nice
it
try.
goes like that.
Ah,
Oh,
11?
wait, 12.
11 or 12?
Yeah.
Okay, put that on the chart.
Okay. Around here.
All right, now I want you to predict. Let's put 3 yellow and 1 blue, and what do you say it's going to be?
Around 40.
40? All right. You say 40. That's 3 yellow, 1 blue. All right, you say 40. All right, here we go.
Well, there goes 5. 10. Well, there's where the other one is.
Yeah, there's where the other one is. So you're all right so far.
There's 16. 20.
Now, where did the other one go before, the long one? 32 it went at.
Around
There's
here's where that
32.
one went. 35. Come
You're
on,
coming up to
40.
40. Uh-huh. Now, how long will it take, however?
45. 50. 55. Minute. Boy, I was way off. Starting
It's starting yet. There. it goes.
there.
1 minute and 6. That's
Yeah.
66.
66. Boy. That's way over here.
Yes. Now, can you draw the line on the top? You know, where this part? Kind of like that, isn't it? What's happening now as we increase the number of yellows?
Well, it's taking more and more
More
time.
and more time. The more yellow we put in, the more time. But so far, what has happened when we put in blue?
Well, it just went
Went
down.
Well, let's
Less
try
time.
3 now. And what do you think it's going to be?
Around 5, I guess.
Real quick, huh?
Yeah,
Much
very
less time. 3, 4, 5, something like that. All right, we'll try it. There's 3 blue. 1 yellow. Now I just knocked the flashlight over. Just a minute. Okay, go ahead.
Oh, there's 5, and it didn't do it. 10.
Mm-hmm. Now I'll put it over here.
10.
Yes, 10.
Not much happened.
No, in fact, you can kind of maybe draw that line up, can't you? You've got something there. Now, notice that a very strange thing is happening.
It's like more or less like a straight line.
Straight line, yes.
Yet this one's curved.
This
some.
doesn't seem to affect the time, and yet this one does seem to affect the time very much. Well, could you please explain that? I don't think you're going to be able to in view of the fact that this is a surprise. But maybe you can think now. Why should one affect the time so much more than the other?
If it's stronger?
How do you mean stronger?
I don't know, more, like more molecules, you know,
Well,
more strength.
that's the right idea. But I think maybe the thing that might confuse you is this. Just because we have one equal containers full of liquids does not necessarily mean that they are both the same strength.
That's why I said it wouldn't work,
Yeah.
and it did work.
See, they may not be the same strength at all. In fact, one might be quite concentrated and the other quite weak. And what is it that's really making the difference in the chemical reaction? The water?
The amount of it.
The amount of chemical dissolved in the water. See, that's what makes the difference. Well, now, with that explanation here, look out, come on over on the other side, because I'd like to see if I can show you now what is really happening with this famous iodine clock reaction. And here is a sort of quick, easy explanation of it. In the blue solution, one in the dark glass, there is an iodine compound. See that I there?
Yes.
That means iodine. Hydrogen, iodine, and oxygen. Now, in the yellow solution, or the light cups, is this and starch. See? Now, when you put the two together, they react. And they form HI, like that. Okay. Now, the minute the HI comes, this reacts with it, like that. You know what you get? Iodine.
Just plain iodine?
Yes. And you see the starch that's in the yellow solution? That could come over and react with this, and we'd get our blue color.
Oh.
But before that can happen, this compound here is much more active than the iodine, than the starch over there. So it comes over and combines with the iodine. And you know what it forms?
HI again?
Yes, hydrogen and iodine together. Well, the minute that happens, this stuff comes over here and reacts with that to form iodine again.
Oh. So this continues and continues.
Continues on and on and on and on and on until, you know, it goes down here, HI again, and this comes down and reacts with it. And from this we get, finally, wait a minute, that goes I. This comes down and reacts with the I, comes down here to form iodine. And when there's no longer any more of this left, then
Oh.
the starch, and what happens?
Black.
Blue, really.
Oh.
It's really very dark blue. So that's why it takes so much time. So which is going to be the important thing to control?
The yellow?
The iodine or the starch and this material right here?
The yellow, I think.
Yes, this yellow. The yellow solution now, the more of it is, the longer this reaction will last. Go back to your chart here, one. Which is the one that made it last a long time?
The yellow.
The yellow, yes. Yeah.
Oh.
So that's the scientific explanation for why that clock reaction will go on and on and on and on and on. Okay?
Yes.
Well, now, let's try some other tricks with it now. We've had fun doing it. Let's try some tricks with it. And here's how we can do that. Here is a, you know, my little stirrer? It's a magnetic stirrer inside there. See? And here, we can put a flask, and inside there's a magnet. And you want to turn that on? Now it spins around. Now, if we put in a blue, and we put in a yellow,
It'll turn black.
16 seconds later, black, right? Or blue. Well, you watch it, see if it does. I didn't start the clock, but you know it should, there,
Yeah.
see? Now, what'll happen if I put in another yellow? I'll put in some more of that thing that, you know, that attacked before the iodine had a chance to react with the start.
Oh, uh-huh. There, and it went right again.
Okay, watch it now.
Gee, now it'll...
Now, tell me,
right.
what are the things that affect the chemical reaction? Have we found out so far?
The heat,
The heat.
the amount of it.
Yeah, the amount of it.
That's all.
Well, there are some other things, too, which we haven't talked about. The acidity. Sometimes it depends on... In fact, in this blue solution that has the iodine in it, it needs just a little bit of acid, or it doesn't, or it won't work. What'll happen if I put blue in?
It'll stay the same.
Didn't change.
No.
See, it didn't quite make it that time,
No,
huh?
not quite. This one will.
Think so?
No.
No, come on. Try another one.
There. That
Well,
one
you see,
will do it.
here I have the actual powders, so I can put the powders in and make it change one way or the other. Here's the powder that was in the yellow solution. Watch this.
Oh, look at that. It made it clear.
I pulled out my stirrer.
There it is.
Now I'll put something in that that makes it turn black. You know, the blue one. Now watch.
Mhm. Not enough. Ooh, look at that. Right down the middle.
See how? Well, that's because the concentration is greater, on the iodine side right there. But as soon as it gets over to the other side, where the yellow solution is, then of course it turns it again. Now I can turn it all the way by putting in enough of it. Yeah, that went that way. Now I can turn it back again. Anyway, you see all the fun you can have by investigating all the
There it goes.
seemingly strange things that change a chemical change.
Watch Mr. Wizard is presented each week at this time by the Public Affairs Department of the NBC Television Network in cooperation with New York University.
Form something else.
Well, would you try to take these apart? Would you like to try that? I think they're pretty
No.
close.
They're pretty close, but they didn't form something else.
How do you know? They formed a white powder that's got...
But it was white before.
Oh, I see. What? Oh, what do you mean by chemical change, then? Maybe we better define that. How do you know when something has reacted chemically?
Oh, wait, it gets different.
How do you mean now, different?
Well, the heat is given off,
Might get hot.
color changed,
Yes, could change color. What else?
smoke.
Smoke or, gas or something like
Yes.
that. Yeah. There are a couple of other things, too. Well, there's no chemical change here, then. Nothing
No,
happens.
you're just mixing them together.
Well,
They're
what would you
just
suggest I do, then, if you said I should mix two powders together?
Add water. Add water.
All right. Can I do that? Before we add the water, however, I would like to put in a little detergent. You'll see why. Okay, you want to stir and I'll add the water. Is the chemical reaction taking place? Hmm?
I think so. Yeah, yes.
Why? How do you know?
Well, it changed colors.
Yeah, well, of course, that could be simply because we're stirring it up. Now, see those bubbles?
Mm-hmm.
Think that's just from the detergent?
Maybe that's the chemical form?
No, see what's happening? In other words, if you put in just plain detergent into water, I'll add a little more to make sure that we're getting enough. Hang the expense. Now let's begin. How do you know that there's a chemical change taking place?
Well, because there's another something else is
What?
forming.
What?
The mixture of the two.
The gas.
Oh,
Yeah,
yes.
see, the gas. Those little bubbles.
Oh, look at it.
You know what those bubbles are filled with?
No.
Yes.
Yeast gas?
Yeah, well, no, that's right, yeast gas.
something?
It's carbon dioxide. And what we have just made, what is a chemical change?
Chemical reaction.
Yeah.
No, but
That's
it's when you have like two chemicals
Mm-hmm.
and you mix them together
Mm-hmm.
and they form something else.
Well, maybe I better do that and see if that'll fit your definition. Here are some household chemicals. They'll work, won't they?
Yeah.
Here is one, and it is sodium bicarbonate. Chemical?
Mm-hmm.
Okay. Here's another one, tartaric acid. A chemical?
Uh-huh.
You call it cream of tartar.
Right.
Okay. I'll put about a teaspoon or so of that in. Okay, now you said put two chemicals together, and they produce a chemical change.
Mm-hmm.
I don't see anything. Powder.
That's not a chemical reaction. These are like just next to one another.
Well, that's what you said I should do, didn't you?
But in chemical reaction, the chemicals they go into one another like and they
Together. But before you do, I want to bring this clock around, and I'll start the clock the minute you pour. Go ahead.
Okay. You know what's supposed to happen? Is this that?
Well, you'll see.
It
You
should
watch
be
that.
black. Well,
What was that former time?
16.
Didn't stop the clock. Was it about 16?
Yes.
16 or 17?
Yeah.
I have to hold it tight up there. Okay, now, you said it was supposed to turn black, and it did. But notice that it turned black 16 seconds after you
I
poured the
know.
two together.
Not the instant I did, and the same time as the other one.
Okay, well, later on, you're going to be able to mix those two solutions together and vary the time to be anything you want. You want it to go in 20 seconds? You can do it. 5 seconds? You can do it. You not only will be able to do that, but you'll be able to predict what time it's going to go in, even if you haven't chosen the time. Because this is a special kind of form of chemical reaction or chemical change, and that's what we're going to investigate today. Maybe when we begin, you ought to tell.
Watch Mr. Wizard. That's what all the kids in the neighborhood call him because he shows them the magic and mystery of science in everyday living.
Wizard.
Oh, hi, Irene, come on in.
Hi.
Come on around over here.
What are you doing?
Well, you see that stopwatch or big clock?
Mm-hmm.
See what it stopped at?
16.
About 16. And you see that dark liquid?
Yep.
Well, that's sitting in front of a little thing here. If I put this in front, now notice what happens to the clock.
Well, it's moving.
Yes, the clock starts. Would you take, see, I have these little paper cups, like they have lemonade at picnics. One of them's dark color, blue, and one other is yellow,
Yeah.
lights. Would you pour those two together?